Good day again to everybody. So the last time that I have given a video lecture, I have discussed there what a proposition is. And as defined, a proposition is simply a declarative statement that can either be true or false. And a proposition can be represented by a capital letter. And together with the definition of the proposition, I have also included there some connectives for propositions. And what are those? We have our negation, conjunction, disjunction, conditional, and our biconditional. And of course, for each connective, so for example, for the negation, we can use this to a single proposition. So let's say we are given the proposition P. We can consider not P. And we have also introduced our truth values. So for any given proposition, by definition, the proposition can either be true or false. Therefore, if we want now to get the negation of our proposition, if originally it is true, then that now become false. If the original proposition is false, then that will now become true. Then we have the conjunction. So we're just doing a review. For the conjunction, we have two propositions, let's say P and Q. We would like to combine them. We use P and Q. Thus, if we now create the truth table for this, so if we have two propositions involved, the first proposition can be true, second proposition is also true, or first is true, second is false, first is false, second is true, or both propositions are false. And this can easily be remembered if we have the conjunction. So just remember and. So this will be true if and only if both propositions are true. Otherwise, P and Q will be false. Then for the disjunction, again, we have two propositions P, Q. We now use our connective or. Again, to remember this, we now take the possible truth value and then we use or. So this will be true if at least one proposition is true. Both are true. P or Q must be true. We have one proposition here is true, one proposition here is true, both propositions are false, therefore P or Q will be false. Then we have the fourth one, the implication. Two propositions again, PQ. Then we have P implies Q. 1, 1, 1, 0, 0, 1, 0, 0. How did I explain this? For the implication statement or the conditional statement or the if-then statement, this depends on the conclusion part. The example that I have given here is, if you pass discrete math, then I will give you a laptop. Therefore, looking at this combination, if you pass discrete math, then I will give you a laptop. If I fulfill that promise, then this must be true. The second one, if you pass discrete math, but I don't give you or I don't buy you a new laptop, then I did not fulfill the promise, then the entire statement is false. But if you now fail discrete math, but still I give you the laptop, then I have fulfilled my promise, then this must still be true. And for the last one, it's just the reverse of both propositions being true. You did not pass discrete math, therefore, I will not buy you a laptop. Then that must be true. And how do we remember this? I have mentioned last time that to remember P implies Q, we always look at the first proposition. If the first proposition is false, automatically P implies Q is true. And then, if the first proposition is true, we now look at the second proposition. If the second proposition is also true, then P implies Q is true. Otherwise, P implies Q is false. The last connective that we have seen is the biconditional using two propositions. Then we have P if and only if Q 1 1 1 0 0 1 0 0. I have shown how the truth values of P if and only if Q were derived. And what are the values here? To remember this, if the entries for our propositions are the same, both are true, this must be true. If P and Q are both false, this would still be true. If one is true, one is false, this will be false. So those are the connectives that we have discussed last time. And also, I have mentioned last time that we can actually combine propositions together using connectives, giving us compound propositions. Also, we can have what we call logically equivalent propositions. Okay, but before we go to logically equivalent propositions, let's go back to our compound propositions. So for today, what I'm planning to do is to give you some examples on establishing the truth table of compound propositions. And let's have the first example for today. Create the truth table for the compound proposition. So let me find a good example here. Let's say we have, wait, I'm looking for a nice example in my file here. Let's say we have find the truth table of P implies Q and P. So we want now to find the truth values for this compound proposition. So to do this, we have our propositions P and Q. We have again 1 1 1 0 0 1 0 0. This is our final compound proposition. So we already have here P. We need Q. We need, sorry for that. We need Q and P. Q and P, we're using the conjunction end. If both are true, this must be true. Otherwise, this must be false. And then, if we now have P implies Q and P, what do we now use? Looking at our table, We now use the first column and the third column. The connective that we will use is the conditional if-then. First column, second column. And if we have the connective if-then, we look at the first proposition. If the first proposition is false, automatically this must be true. If the first proposition is true, we must check the second proposition. If it is also true, this must be true. But if the first proposition is true and the second proposition is false, then this must be false. So that's the truth values for the compound proposition P implies Q and P. So for today, I would also like to give an example wherein there are 3 propositions given. So last time, we only limited our discussion to 2 propositions. So for today, what if we now have 3 propositions? So instruction, write or determine the truth values for P or Q implies a third proposition, not R. So 3 propositions. Since there are now 3 propositions involved, let's write them down. P, Q, and then R. And we look at the truth values of each. So if there are 3 propositions given, all the propositions can be true, or the first 2 propositions are true, the third is false. The first proposition is true, second proposition is false, third proposition is true. Or first proposition is true, second proposition is false, third proposition is false. What else? We can have the first proposition is false, second proposition is true, third proposition is true. Or first proposition is false, this is still true, third is false, or this is false, this is false, this is true. Or the 3 propositions would be false. So, how many all in all? We have 1, 2, 3, 4, 5, 6, 7, 8. Okay? And actually, if you have 3 propositions involved, the number of combinations that we can have here is 8. And how do we get that? Actually, there is a general rule for that. If you have n propositions, to determine the possible number of combinations, we use the formula 2 raised to n, where n is the number of propositions. So if you will go back to the list, if you have 2 propositions, 2 squared is 4. If you have 3 propositions, you have 2 cubed. 2 cubed will be equal to 8. Of course, as n gets larger, we have also a number of the possible combinations. But for our discussion, we can just limit our discussion up to 3 propositions. We have propositions P, Q, and R. So what do we need? We need P or Q, or at least one is true for this one to be true. So we're looking at the first 2 columns. Both are true, this must be true. Both are true, this must be true. P is true, P is true, Q is true, Q is true. Both are false, both are false. There you go, for P or Q. Next, we need not R. Okay, let's write here not R. So we just negate this. That will become false, true, false, true, false, true, false, and true. Then finally, for this proposition, so let me just copy that using an arrow. We now look at the fourth column and the fifth column using the connective if then, or the conditional connective. And what's the rule? If we are using the conditional connective, we look at the first proposition. If the first proposition is false, automatically this will be true. But if the first proposition is true, we check the second proposition. It must also be true for this to be true. But this is false, therefore this must be false. Both are true. This is false. Both are true. This is false. Both are true. Therefore, this is now our truth values for the compound proposition. And by the way, to make things more orderly, if we have three propositions so that you will not be confused in writing down the possible combinations of the truth values for each of the three propositions. This is how you will remember it. Look at how we have written down the combination. For the first proposition, since we have a total of 8 combinations, for the first proposition, we divide it into 2 groups, 4 each. 4 true, and then 4 false. Okay? 4 true, then 4 false. While for the second one, alternate 2 each. True, true, false, false, true, true, false, false. And then for the last proposition, alternate true, false, true, true, false, true, false. So that will always be our order so that it will be easier to remember. Okay? But if we have only 2, again for P and Q, how do we remember this? True, true, false, false, alternate for the second. So if there are 2, true, true, false, false, alternate for the second. If there are 3 for the first one, apat na true, then apat na false. And then here, tagda dalawa, then for the third, alternate. Okay? One more example. One more example for finding the truth value. And let me now find the truth values for P or Q and P or R. How many propositions? We find 3. So let's list down P, Q, R. There are 3 propositions. So for the first, tig-apat. Apat na true, apat na false. Yung sa second, tagda-dalawa. Dalawang true, dalawang false, dalawang true, dalawang false. For the third one, alternate. True, false, true, false. True, false, true, false. And then, what do we need? We have P or Q. If one is true, this must be true. P or Q. There you go. This is true. This is also true. Both are false, therefore this must be false. Both are false, this must also be false. And then we need P or R. P or R, first and third. This must be true. This must be true. This must be true as well. This is also true. This is true. Both are false. This must be false. This is true. Both are false, so this is false. And then finally, let's just put an arrow there. Mahaba, hindi siya kasha. We now look at the fourth and the fifth column. Our connective is AND. So if our connective is AND, both must be true for this compound proposition to be true. Both are 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 true. One is false. One is false. Both are false. This would still be false. So this will now be the truth value for our compound proposition. Okay? So I hope you're able to follow what we are doing. Okay, then I guess I will end the presentation here. I'll just do again another video for logically equivalent proposition so that this video will not be that long. So I hope you have understood this. Again, if there are questions, please feel free to ask me through Messenger or through email.